All right. Today is the 23rd, and so we are going to continue talking about, well, it says here memory management. We're going to finish off constructors and destructors and then move into memory management. In terms of what's due, tutorial 3 and assignment 1 are due this weekend. There has been an update to assignment 1, sort of a weird little bug. If you run it on the VM or OpenStack with a max array size of 256, you're going to get a stack overflow. It won't come up as a stack overflow, it'll come up as a seg fault, which is interesting because I thought I was really using the same version of the compiler, but apparently not. Right, so I dual boot my machines, and so I have a Linux partition. It's Linux Mint, but it's built on top of Ubuntu 20.04, I think. And apparently, there's differences in the stack sizes between that instance, which is unexpected, to say the least. Anyway, so the fix is to, in defs.h, there's a preprocessor constant called max array. You change that to 100 or some reasonable value. So yeah, my apologies for that, but like I said, it was sort of not expected whatsoever. Questions on that? So if you download the starter code from Brightspace, it's there. There's an announcement posted that has the new defs.h, or you can modify it yourself. It's very simple to do. Okay, so that brings us to what we were talking about last class, so constructors and destructors. And so just to sort of sum up where we are right now, right? So if I make a class, any sort of very simple class, and I could put like int x, y, and that's it. So that's a class. Those are private. This is not a very useful class, but let's say even I can make them public. What I've not defined is a constructor or a destructor or a copy constructor or any of these things. Well, in this class, I get all of those for free. I get a default constructor, which means that all that means is that I can make an instance of my class, right? It's not going to do anything useful. It's not going to initialize my variables. If these are objects, it would call the constructors on these objects. But it's not going to do anything. It's not going to take any parameters or do any of that stuff. I get a default destructor, which means I can just destroy my object. Okay, so these default things don't do much, but they do allow you to do some basic functionality. I get a copy constructor, which will make a byte for byte copy of this object, right? So in memory, this is really just a struct. And if my struct is whatever, so in this case, these are 32-bit or 4 bytes each. So this struct is 8 bytes. And if I make a copy of it, it will also be 8 bytes, and it'll copy exactly byte for byte these two values. And then I get an assignment operator, which does exactly the same thing, except in this case, I have an instance of this class that's pre-existing, and I copy it over. Okay, so those are the things I get for free. And so then we started talking about constructors, right? So, well, a funny thing happens. I make a little bit of space here. Let's say I make a constructor that takes int x, int y. Well, now all of a sudden my default constructor is gone. Okay, it gets deleted. So I'm not allowed to, I can still make a class, an instance of a class A, but now to make it, I have to explicitly supply these values x and y. Okay, so I get a default default constructor as long as I don't have as long as I haven't defined any constructor. As soon as I define a constructor, this gets deleted. Now I can make my own, right? I can make a no argument constructor. I can add a no argument constructor here. Or I can give these x and y default values. I can say this is equal to 0 and this is equal to 0. And then that means I can make an instance of this A class without supplying any arguments. Okay, so that's basically where we left off last class. And I still, in the background, have all of these three things for free. And so then we talked about destructors. And so constructors have one purpose, initialize all the data members. We talked about destructors, which look very similar to constructors. Their responsibility is to clean up resources. For simple structs, we don't really need them. Or we can use the default because we don't have to do anything special. But if we do make one, it gets called for us implicitly, right? So basically, it gets called when a locally declared object moves out of scope. So I declare an object inside a block. I exit that block. The destructor is called on that object. At the end of the program for global objects, right, we saw thing 1 and thing 2 were global objects, and they don't get destroyed until basically I'm done my program, and then those get cleaned up. Or when I call delete on a dynamically allocated object allocated with new. I don't remember if we did that example in this class, but we will see instances of it coming up. All right, so that is about where we left off. One of the things I probably didn't mention, sorry, I get this mixed up with the other section, but there are, right, ways to sort of prematurely exit my program, right? Something goes wrong, I have these options, exit, and I can pass like a, you know, an error code. So I might say exit 1. And that's going to return a 1, which means something, right? I don't know. Usually means that we exited with an error code. Probably it gets more specific than that, but I haven't looked at that in a while. If I call exit, well, local variables do not get destroyed, right? The stack is sort of abandoned, but my global variables will still get destroyed. And if I call abort instead, well, then something went really wrong, and I basically want no destructors to be called. Okay, so that might be the special case of maybe my destructors will save state, right? So I'm running some program, and then if I exit, I want to save all of the current running parameters to disk. But if I notice those current running parameters, something is really very wrong with them, then I probably don't want to save them to disk. And so I have an option just to just bail out and hope when I come back and rerun this program that things are in better shape. All right, questions? That's just basically review stuff. Okay, so today we're going to start with copy constructors. So copy constructors are sort of, they appear a lot in C++, which is kind of weird because they don't really make an appearance in Java at all, right? So C++ and Java kind of went different directions. C++ by default, in a lot of cases, will make copies of stuff. And to make copies of stuff, well, generally speaking, as mentioned, we get one for free. So I can make a copy of something, an object, a date, or whatever. But I can also define it explicitly. So if I define it explicitly, then this is the function signature. So let's say it's a date class. I'm going to pass in another date class by reference. This is important, this part here. It will not take a pointer, will not take an object, right? And in fact, maybe we will talk a little bit later, if I remember, about why this is such a bad idea. That won't work, but if it did work, like what would happen? So we'll think about that, hopefully come back to it. Last section, I said I would come back to it, and I completely forgot. So we'll see if I remember today. The other acceptable function signature for a copy constructor is this, where I have a const object, right? So we're going to talk about const. Const essentially means I can't modify this incoming date parameter. We'll get to that a little bit later. Anything other than the above, the compiler will not recognize it, and you may say, well, who cares? Right? I can just make any old constructor I want. So what's special about these? Other than they take an instance of themselves. Well, what's special about these is these will be called implicitly in a lot of situations, right? So there are a bunch of ways to get your copy constructor called. This is the explicit way, which means that I am making a date and I am explicitly passing in another date as a parameter. But there's a whole bunch of situations where the copy constructor gets called and it looks nothing like this. All right, so it gets called implicitly and sometimes in unexpected ways. All right, so our copy constructor is provided by default, performs a member-wise assignment. I'll give you a brief overview of what that means. So let's say we have our class A. It's really a struct, and in memory there's two ints, right, 10 and 12. So this is our class A. Our copy constructor will allocate the same amount of memory. We'll call this, whatever, it's still a class A. Allocate the same amount of memory, and then it just does a byte for byte copy, which means that these two integers will also be 10 and 12. And for a lot of objects, that's great. We don't need anything more than that, and this works perfectly fine. The problem comes if I want to do something like this. Maybe I have a pointer to an int instead, right? And so down here I have the heap, and on the heap I have this pointer, this integer that I've allocated, and it contains the value 12, and this pointer points to it. Okay, so what is being stored in my class A now is an int with the value 10 and a second int with the value of a memory address. So my default copy constructor does a byte for byte copy. Well, it's going to copy this memory address, and now I have a pointer pointing to here. So I have two objects in memory that are sharing a reference to a single int in memory. Okay, so maybe that's what we wanted, but often that's not what we want, right? What we probably want is something more like this, that I make a copy of this, I copy in the value, but I actually get the new memory address, so this pointer points to a unique object on the heap. Okay, so there's many reasons why we might need a copy constructor, but this is probably the one that we are most concerned with. Right? We have dynamic memory, we are pointing to dynamic memory inside of our object. When that's the case, we probably need to make a copy constructor. Okay, so in the first case, where we did the byte for byte copy, that's called a shallow copy, right? Which means that if I have a pointer, I just copy the pointer. So now we're both pointing to the same thing. This here, where I follow the pointer and I make a copy of the object that's being pointed to, that's known as a deep copy. Okay, so that is the main reason why behind a copy constructor is that I write one because I want to make a deep copy, right? The shallow copy is not what I want to have happen. We're also going to look at a conversion constructor, but just for completeness sake, I've not found a use for a conversion constructor in our assignments. I don't know. Maybe I'm just not clever, or maybe I'm not being imaginative enough, but we will look at it just for the sake of completeness. Okay. Questions on this? All right, so usage. Well, when do the copy constructors get called? Well, there's a few cases, actually. We will actually dive into the example. I think that's the best way to show it. No. Stop. What is this? All right, whatever. No, that's not what I want. I want the copy constructor. Okay, so I have here a song class, and there's nothing. It's got every song has a title and an artist. In this case, it also has an ID, just so we can sort of recognize. Well, whatever. These are all just identifiers for our song. Nothing special about the constructor. I initialize all of these values, and I announce that I'm in the, let's not use the word default. Let's just use the normal constructor. And down here, well, we've also defined a copy constructor and a destructor, right? So in our copy constructor, Well, the destructor doesn't do anything for the moment because I don't have any dynamic memory in here, so I don't really need a destructor, but I'd like to know when this thing's being destroyed. So I made a destructor and I announced, hey, this thing is getting blown up now. My copy constructor, I'm taking this song passed in by reference and I'm grabbing the song ID and I'm copying it into my ID. And the song title and I'm copying it into my title. So I'm just using the assignment operator and I'm doing what the default copy constructor would have done, right? There's nothing, I do not need to write this copy constructor just to do this because this is pointless. It will do this for you automatically. But we wrote it anyway because we want to see when it gets called. Okay, so we're going to announce when we make a copy of these songs. And so we'll see exactly the syntax where it gets called explicitly and where it gets called implicitly. Let's say I make a bunch of songs. I make 4 songs here, and then I'm going to, I don't necessarily like the order that these are in, but we're going to start with this instead. So I'm going to make a song called S7, and I'm going to explicitly pass in S4 as a parameter and print it out. Actually, before we do that, let's just do a quick run of making the songs and printing them so we can see what's going to happen. Okay. So when the songs are made, we call the constructors, we print out all of the songs, and then the songs are destroyed on the way out. All right, so down here, we're going to make a copy of song 4 with an explicit call. And here we see explicit call to copy constructor, and we're in the song copy constructor. We print out this song, and it was here. Well, it's always nice sort of to explicitly label all of this stuff so that it's easier to read. So we're going to print out the song, we're going to copy the song, and then we're going to print out this song that should be a copy. All right, so song to be copied is this Motley Crue song. We make a explicit call to the copy constructor, and we print out the copied song. It's Motley Crue. So wonderful, it worked just as planned. Nothing too special about this, though. This is an explicit call. Now we're going to get to the implicit stuff, which is where the problems can arise. But questions on this? Okay, so one implicit call is this. So this is weird. And there's a name for it. I cannot remember the name. It's like something initializer syntax. But I forget because there's a bunch of things that are called initializer syntax. So I forget the exact word that should go in front of that, but this is, I declare a song S5, and in the same line, I assign it S4. Okay, so this, I'm going to put here, song to be copied is S4, calling the copy constructor, and then printing S5. Okay, so song to be copied. Again, it's the Motley Crue song, calling the copy constructor. The copy constructor does get called. This is an implicit call though, right? Because I didn't actually pass it in as a parameter. I just did some syntax. The compiler did some syntax magic here, right? It looked at this and it substituted this essentially. But this is an implicit call. Okay. All right, questions? Okay, so let's get to this may or may not cause problems. One thing that quite often causes problems is, where is it? All right, well, I have two functions. I have a pass by value function. So I take a song, I pass it in as a parameter by value, right? So there's no reference, no pointer here. And then I have a pass by reference where I pass in a song by reference. So apparently I didn't set that up for some reason. So I'm going to just quickly say passing S3 by reference. Let's do it a little bit differently. Okay. So what does pass by reference and pass by value do? Well, they just print the song inside there, and then we return. Okay, so then let me also just clean things up a little bit here. All right, so we're going to make the four songs, we're going to print them out, and then we're going to pass this song 3 by reference. Okay, so it goes in there, it gets played. You'll notice the copy constructor was not called here. Okay, so pass by reference. Well, what actually got copied was, of course, the memory address, as we talked about before. Behind the scenes, this is actually passing in a pointer, right? So when the compiler looks at it, this looks like a pointer. For us, it's a reference, and when we handle it as we would any variable, right? We do not use pointer syntax. All right, so let's change that to pass by value. Okay, when we pass by value, a copy is made. All right, so this can have a bunch of side effects. So especially if you have dynamic memory and you have not set up your copy constructor correctly, right? So this is a source of many bugs. In general, you never want to do this unless you know what you're doing, unless you have a very good reason to do it. So by default, every time I pass an object, it should look like this, or a pointer. If I do this, I should be able to justify why I'm doing this, because this is not a good idea by default. Okay, there's maybe situations where you would do it, but generally those are bad. So if I was in pass by value, and let's say I did s.set, do I not have that? Set title, yeah. To, yeah, I don't know. It's famous, but it's not heard. I don't even know if it's a song, to be honest. It's kind of before my time, but so we're passing in this by value, we're changing something about it, and then we're returning it. So inside of my pass by value, I've changed the title, and that title is reflected, the new title is reflected when I print it. When I return, I print that song again, but now it has the original title. Okay, so one of the things that happens on your assignment 2 when you start passing around arrays of things, or rather data structures that contain arrays of things, is that you pass by value. So you pass in this array and then you add something to it, and then it returns, and your array does not have that thing. And in addition to that, you've deleted like the backing array, right? So this, anyway, so don't do this unless you know you have a very good reason for doing it. Do this. Questions? Yeah.
I don't get why when you pass by a reference, like it doesn't print out.
Which doesn't print out?
Like pass by reference, like when you like run the program, it doesn't print out.
It did. Let's do this. You mean inside the function? Is that so passing song 3 by reference, I get this is song 3 is Black Sheep. So it did get printed out in there. Yeah.
With it will get saved because it's by reference.
Exactly. Yeah. So exactly. So if I did this same thing, when it gets printed again, it'll print once here and then once when we return, and they will both say Dark Side of the Moon. So I did not save that correctly or what?
Yeah, you have unsaved file.
I have one unsafe file. It's over here though. What did I do here? Oh, yes. Very good. So yeah, so now the changes are reflected in the original. So yeah, I've passed in the actual object, I passed in the memory address, and then I changed the title, and then when I return, the title is changed. Whereas in the other case, it's not.
But why would you name it like the new name? Like, aren't you doing a copy and then changing the name of the copy?
Yeah, that's exactly what we did. So I guess just to explain exactly what happened, I call this pass by value function. I make a copy of the song. I change the song title to Dark Side of the Moon, and then I print it, and that gets printed. I'm returning from that function, and as I return, that copy gets destroyed. And then I print out the original song. This is the song that I passed in, but I passed in by value. So it made a copy, it changed the copy, but then it deleted the copy, and this still was never touched. Yeah. Yeah. Good stuff. Any other questions? Okay. Tons of painstaking detail here. I think a lot about how to, I really do spend a lot of time thinking about how to make this class more interesting, because I know not everybody likes diving into detail for 80 minutes at a time, but I don't know. If you have any ideas, float them by me. I'll definitely take them into consideration. So yeah, those are this is the big, well, there's two of them really, right? So there's this, which is an implicit call to the copy constructor. Maybe not such a big deal, but this is the one that gets people, right? Especially in this class when you're still learning. When I pass by value, it's going to get a copy, and then all kinds of bad things can happen from there, because that's not what you intended to do usually. Okay. In addition to that, you can think of return parameters. So I have this return by value. And so I make a song on the stack. Now, if I return that by reference, that's a problem, right? Because I'm returning the memory address of this song, but this song is getting destroyed as soon as I exit this function. So if I'm returning, I really want to return by value, right? So the return variables are kind of the opposite. Not really, but there is a strong justification for returning by value. And you'll see actually what happens is that, well, the compiler is actually smart enough not to make a copy of it. So if I do, let's get rid of all this stuff. So I'm just going to make a song S9 that's going to grab this returned by value song. I guess I'm not even printing it, all right? So probably nothing's going to happen. Did I not compile this? All right, well, let's s9.print. Okay, oh yeah, sorry. These are just the regular prints. I go in, I make a call to this function, this return by value. I make a new song, and no copy is made. All right, I've returned it by value, but no copy is made. That's because the compiler looked at your code and realized, well, why do I need to make a song here and then copy it back into this other song? I will just create it here. So the compiler is doing an optimization. But you know, in theory or in the model that we use, this would make a copy, right? So you can kind of think of it as I am allocating a song on the stack, and then I'm going to return it by value, which is going to make a copy of it, which means that, you know, it'll preserve all the values, but I won't have a reference to some dead piece of memory, right? So return by value is actually pretty valid. Questions? Yeah.
On Xamarin test where it's like that's a bit of code and then this function we'd say copies this by key.
Yeah, we're not going to focus too much on the returns. So return by value is generally going to be acceptable for almost all of our use cases. I mention it here because, again, there's a bunch of surrounding stuff that I'm going to teach you, sort of relevant if you get a job in C++, but I'm not, because again, it is confusing, right? Like you would think it would make a copy, and if you have a different compiler, it might. In this case, it doesn't. So yeah, I'm going to focus on the parameters, the return values. We're just going to do what's convenient, not necessarily what is the best optimized thing to do. Yeah. So yeah. So I won't ask that question, I guess, is the short answer. Other questions? All right. Okay, so if I want to, I can put in this keyword, explicit. Because some of these can be tricky. So if I put in this keyword explicit, and let's now bring some of these back, pass by value. So I'm now making a copy here explicitly. I'm making a copy here implicitly. I'm making a copy here implicitly. And I'm making, well, I don't even know if that'll get flagged actually, but let's see. So I added explicit, and now the compiler says, well, actually, you are not allowed to do this. And in fact, in this version of the compiler, C++, so useful. Eh? The compiler is, well, I tried to turn it into an int and it didn't work. It's like, is that a really useful error message here? Really, I disabled this implicit call to the copy constructor. So that's why this didn't work. The compiler is trying weird stuff to get it to work. Down here also, cannot convert song to int. Again, so silly, but yeah, that means that is a byproduct of saying do not make implicit conversions. Also down here, I guess it did flag this, even though no copies were made. Technically, we're calling the copy constructor implicitly. That's actually kind of interesting. But yeah, question. So explicit disables all of those other cases, and then I can only use basically this one, and which is kind of nice because this is sort of like not error prone. But yeah. Questions? Yeah.
Listen, exactly.
So in the declaration, I can say explicit. I mean, I can put it on any constructor, and we'll see why. Actually, we'll see a couple other use cases for this. Other questions? Yeah. That's a good question. And with that, I doubt it, but you never know. So that's the key is that you only allow this one. So yeah, you're only allowed one destructor. it has 0 arguments. There's no conversions going on. So I don't, it may not be a syntax error, but it may be like, it may have 0 effect. Let's see. No, only declarations of constructors and conversion operators can be explicit. Okay, so it's just, yeah, this is meaningless, I guess, and also a syntax error. So yeah, good question though. Other questions? Okay. All right. So much time on copy constructors. So conversion constructors we're going to look at, probably we'll never use them in this class. I don't know. I've never found a use case for them. Maybe I'll try and think of something. But basically, again, I'm going to take, it's similar to a copy constructor, except now I have 2 different classes. So I have a class A and a class B, and I want to take the data from class B and use it to initialize class A. For example, if I have a date and a date time, well, maybe I want to initialize the date part of date time with a date object, right? So again, I mean, I can make any type of constructor I want with any arguments I want, but if I use this specific syntax, then it will get called implicitly for me. So conversions, if I pass by value, this will get converted. Like if I pass a date by value into a date time parameter, I'll automatically get converted for me. Again, yeah, so let's take a look at that example. So here we have songs again. One thing I guess didn't mention is that in this, but it should sort of be clear, I passed in a separate song by reference, and then I accessed that song's private member variables. Okay, so you're not allowed to do that in Java. You can set up a function in your song class that takes another song variable, but you cannot access the private members. But here you can, and it's not just this function, it's any function. All right, so there's one thing to note. I was able to make a copy very quickly and efficiently because I have full access. Whereas for a conversion constructor, of course, well, now I have a song and I have a music video. All right, so I'm going to take the information from the song, which is the title and the artist, and I'm going to add a third parameter, which is I don't know, sort of a meaningless. I couldn't think of anything, so length. I'm going to add a third parameter, but I want to initialize this video sometimes with the title and artist from an existing song. All right, so I made here a conversion constructor. The key to this is that I don't have private access, right? Even though I want to convert, I can do things like make it a friend of my class, which we'll see later, but until we get there, I have to have some sort of public accessor to these member variables in order to get them inside this constructor. Okay, but other than that, this follows a lot of the same pattern as before. We're going to declare when we're in the, let's just call this normal constructor, and we're going to declare when we're in the conversion constructor. And there should be we'll try and go through it fast because there should be very few surprises, but we're going to make a bunch of songs, and then, well, we'll start by just making a video without a conversion constructor, just to make sure it works. All right, so we made a bunch of songs, and then we created a video. We called the normal constructor. We printed it out. I have some weird pieces of code at the end here that I forgot to disable, but that's fine. So you can kind of ignore everything else. And then at the end, the video and all the songs got destroyed. Well, here I want to make a second video out of a song. So this is an explicit call to a conversion constructor. And song 2 is, what is it? I don't even know. Song 2 is the dirty nil, so the pain of infinity, and we converted it into a video. All right, using an explicit call, again, kind of what you would expect to happen. Any questions? Well, we can also do implicit conversions, right? So I declare a video and I assign it a song in the same line. Initialization. Maybe it's just initialization. Maybe there is no phrase that I'm forgetting. But yeah, I can do the same thing here. I apologize for the, so yeah. Up here for song 2, I call the conversion constructor, and then for song 3, I also call the conversion constructor. That's this line here. And then printed it out, and then everything got destroyed. Now, this is a little pushed together and tough to read, but yeah. So pass by value, return by value, these all sort of work the way you would think. All right, so yeah. Pass by value, the conversion constructor was called. So this pass by value actually takes a video, and it takes a video by value, and I passed in a song and it converted it for me. Okay. Now, I said you should almost never do this unless you know what you're doing, right? So I suggested you should do this. This will not get converted, right? So if I try and pass it by reference, it's going to say, well, this is a song, not a video. I'm not going to convert it here, right? So this is, yeah, not allowed. So this implicit conversion happens if you pass by value, which I highly advise you not to do unless you have a very good reason to do it. So it's going to kind of like seldom come up. Return by value, same thing, right? If I return by value and inside my return by value, I make a song and I return it, it will get converted into a value. These are all implicit conversions. Well, I can, of course, the same thing I did before, I can call explicit here. And was this working before? Sorry. Just the last thing I compiled was an error, so I wanted to assure you that it does work, and then I add the explicit keyword, and that's going to disable a lot of these things. All right, so now I'm not allowed to implicitly convert anything. All right, questions? Yeah.
Implicit version or like does it first? So, for example, in this case of what it's implicitly converting song to video. Does it create a copy of the song that convert it to a video, or does it go straight to video without creating a copy?
I mean, it's going to pass, so it's going to call this function here, this conversion constructor. So it's going to pass in the song by reference and then make the video, right? So yeah, so it never makes a copy of the song. It makes a new video and initializes it with that song. I think, yeah. Right. Other questions? Okay. Last thing I'd like to show you, because I show you this because this actually is something that I did, and I was very, very confused by it, right? And it's a little subtle bug, but so I've disabled all, I guess I don't even need these guys. All right, so the only thing we have running is this code here. I'm making a song S5 and I'm assigning it an integer. Now I did expect when I did this, yeah, it's complaining because of my, it's basically saying, what are you doing here? You can't do that, so let's take that away. So that compiled just fine, right? So I made a song and I said, well, assign it the value 5, and then I print it out and I get I get called this, I guess, default constructor. And it's the song Unknown by Unknown with an ID of 5. So yeah, this really, so what happened here? This made a song. It called the regular constructor. Yeah. No, 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 those are good guesses though. It did something even, I mean, I think this is one of the, this is a feature that when people talk about like features to leave in C++ or new features, a lot of people want this taken out because this is like wild that you can do this. I find this bizarre. So actually what it did is the compiler said, well, so this is an integer, but if I look at the song constructor, well, it has a bunch of default arguments, and the first argument is actually an integer. So I can actually call a constructor with a single integer, and these will get the default values, and ID will get the value that I sent it, 5. So the compiler converted this into a call to the constructor with 5 as the first value, right? The first argument, which is bananas. I would never have expected this unless I happen to run across it, which I did. So like if you want to be really safe, you can add explicit here. And that will not allow. Now when I try and compile it, it says, okay, you're not allowed to do that. Right? Conversion from int to song, yeah, whatever this message means. It means that I can't do it that way anymore. Yeah.
Experience, it would also have a compilation error, right? Which tries to do the implicit conversion.
Like if I do, so I can take away this. I just want to confirm that this works. Okay, so yeah, still works. But yeah, if I take away this, I'm guessing you're right that we would have a problem because now I need a string. Yeah. So yeah, it really is, if I can sort of reduce this down to one thing, then I can, yeah, I don't know. It's really ugly syntax. I don't know why you would ever do that. You just, it's sneaky. It's weird. But anyway, questions? It's not really. You won't be tested on it. I just thought it was interesting. Okay, so that is constructors and destructors. That takes us to memory management. And in particular, dynamic memory, right? So I'm going to try and, there's a lot of review here. Maybe I'll try and speed it up a little bit. We're going to review a little bit about memory, and then we're going to talk about pointers, and then we're going to look at how we, basically how we handle dynamic memory allocation and dynamic arrays, which is where the real sort of lessons come in. So this is our memory model, if you recall. So this is the global, what is this? The data segment. This is the compiled code. This is the stack. And down here, this is the heap. This is from a system call. All right, so we've gone over all of this. So a little bit about the stack, I guess. If it's not clear by now, let's fully define what a stack is, a stack data type. It's a last in, first out data structure, right? So you can think of it as a pile of things. And every time I need something, I take things off the top. And every time I want to put things on the pile, I put them back on the top. So the last thing that I put in there is the first thing that I take out, just like a pile of dishes. When I add something, it's referred to as pushing. When I take it off, it's referred to as popping. And a function call stack is just a stack where I put stack frames, right? And stack frames contain local variables, parameters, etc. All right, so, right, a quick example, x, y, 10, 12. If I call my main function and I have these local variables x and y, well, these will get stored on the stack, right? Like the stack grows in sort of the opposite direction. And then this is the end of my stack frame. Right? There's generally some metadata there, but the stuff that we care about is generally the variables. If I call this foo function, well, I make copies of x and y. So this is 12 and 10. And maybe I declare a local variable z inside there. Well, then I have 12, 10, and 20, and that's my next stack frame. Then I call this absolute value with x. That takes 12, and so I get 12 here. That's my third stack frame. I return from here. This stack frame gets popped off. Those values are lost. I return from foo back to main. This stack frame gets popped off. Those values are lost. I exit main, and I'm done. All right, so that's basically how your memory works for your function call stack. That brings us to the heap, right? The stack is sort of, I'm dealing a lot with local variables. The heap is like going to persist for a long time, basically until I delete it. So the heap is memory that I have to manage as the programmer. So the stack, when I pop off a stack frame, all of that is handled for me. But essentially, somewhere in my code, I will ask for a pointer. Let's say I have some stack frame, and in here I have a pointer, and that I ask for a new piece of memory, and that pointer is going to point to that piece of memory. And now I can write and read to that piece of memory by using this memory address. Memory address stays on the stack, so I got to be careful, right? I don't want to lose it. If I lose it, that's a memory leak. But yeah, that's basically how dynamic allocation happens. My pointers will be on the stack, generally speaking, or at least one of them has to be. And then I can access the heap that way. All right, so statically allocated memory, if you recall, that's just if I do something like this, date D. There's no new keyword. Memory is reserved in the context. If this is if it's a function, it's put on the function call stack. If it's within another object, well, then it's stored wherever that object is. The important thing is this memory is handled for us. When the context is destroyed, the destructor is called, and whether that's because the stack frames popped off or the thing that contained it was deleted, whatever this, I don't have to worry about the memory for this. Dynamically allocated memory is different. So it's on the heap. I use the new keyword, which returns a pointer, and the pointer is a memory address for memory on the heap. I can do this anywhere. Doesn't matter. And the lifespan is not dependent on the context, right? If I allocate some memory in a function, I return from that function, that memory is still there until I call delete on it. So now the syntax I would use is something like this, all right? And you'll notice in Java, when you declare a primitive, you sort of like statically allocate it. And when you declare an object, you dynamically allocate it. In C++, you can do static or dynamic to either primitives or objects, right? So I can make an int and put it on the heap, and I can make a student to put it on the stack, or vice versa, or whatever I want. Okay. So what is a pointer? A pointer is a variable that stores a memory address. So the address of an existing variable or the start of something on the heap, perhaps an array. Why do we use them? Well, it's a level of indirection, which is kind of nice for a lot of algorithms, but also they're small, right? I want to copy a pointer. It's basically one CPU cycle, give or take. 8 bytes, generally speaking, on a 64-bit system. So often smaller than the data points to, which makes it more efficient for passing parameters. An easy way to avoid copying data. If I pass a pointer, I don't get these, accidental copies being made. All right, so pointers have name, data type, value, location, and memory. So yeah, let's check out an example of exactly this. So I have, assume that these are the memory locations of my different variables, and these are the contents, right? So that's the value stored there. So in my memory map, I have this name C. It is of type char. It has a value of H, or the ASCII code for H, and the memory location is A8. And I also have, an int. It's named I. It is type int. It has a value of 42. and it has a memory location of A9. And then let's say I declared this char star C pointer, and I assign it, well, it holds a memory address, and I want to give it the memory address of C, so I'm going to say ampersand C. My ampersands are terrible, I apologize, but there you go. So that means I want the memory address of this variable. So I have, the name is C pointer, the type is char star. The value is, in this case, I've assigned it the memory location of C, which is A8. Its own location is AA, right? Which means that, that sort of suggests we can have pointers to pointers. And if I did something like this, I did C pointer, well, actually, you would think this would print out a memory address, but this would, but char stars are special, right? So let's put I pointer. If I made an I pointer, a pointer to an integer, then this would print a memory address, okay? And then if I dereferenced it, I would get, well, I'd say, actually, don't give me the value. Follow the pointer to the memory address and return what value you have here. So if I did this for C pointer, it would say, well, you're pointing to this memory address, so go to this memory address here and return this value H, so this would print out an H. Yep. Sure. Yeah, no problem. All right. Questions? All right. I think a lot of this is review, but let's quickly take a look at, I guess, yeah.
If there's error in allocating dynamic memory, does it throw the exception?
That's a very good question. I don't know. And what type of error would you get? That would be, I think, a catastrophic error. uh, right. I'm guessing C++ would do something similar. It is sort of hypothetically based around C, yeah. What does it set? What error code? What?
But it's like it sets the error code in error node, which is usually like in out of memory or something like that by the other system.
Okay. Yeah. So that's, I don't know. So so your explanation is far better than anything I know, because I don't know. I've just never, I guess, never run into that problem. But yeah. So the question was, yeah, what happens if the memory allocation fails? And the answer is I don't really know. I'd have to look it up. But apparently in C, there's a memory code you can look up, and it returns a null pointer. And I'm guessing that C++ does something very similar. So yeah, that's yeah, nice addition to the current argument. Other questions? Also, I have a question for you. Like, are you guys familiar with pointers? Is this sort of useful, this part of the class? Like, was that a handshake there? So yes, no, maybe, kind of. All right, so I'll just try and go through quickly and like maybe highlight a few things. But I think in general, probably you know what pointers are. So here I've declared two pointers. One pointing to null pointer, one pointing to null. Anybody know the difference? Yeah. Yeah. Also, this technically, I believe, can be read as an int, right? It can be read as 0. Whereas this actually has a type. It cannot be read as an int. So technically, this is a little safer. If I said, these are equal though, right? If I asked, are these two things equal, it will return true. Generally speaking, a null pointer is preferred because it has a type, and it's slightly safer than this, but like whatever. You guys can use whatever you like. Yeah, all right. So I guess, sure, let's do this. I'm in the wrong place. I'm in the wrong place altogether. Okay. So sizes, my char itself is 1 byte. An int is 4 bytes. These two pointers are both 8 bytes. Okay, so what that means is that basically if you're passing these primitives as parameters, then you can pass them by value, right? That's not a problem. Unless you want to use them as output parameters, passing by value is at most as bad as passing a pointer anyway. Okay, so ints, floats, doubles, longs, those are all fine to pass by value. Objects, of course, you should still pass by reference. And case in point, if I have this fake class up here that has an array of ints, if I pass by value, well, then I'm copying 44 bytes, whereas if I pass by pointer or by reference, I'm passing 8 bytes. Okay, so one of the, actually, sorry. I do want to satisfy my own curiosity here. So reference, it still reads as size 44. Huh. All right. Well, technically, behind the scenes, that's not what's happening. Of course, if I want to assign my I pointer to point to this integer, I'm going to use the ampersand, that is the address of. And then I can do a bunch of things like, well, I can read the address of I can read the address of my I pointer, and I can read the value of those two things. And just to quickly, so the integer address, the address of I is this, and you'll notice, although it's hard to parse, this is the same as the value of I pointer, right? So this I pointer is pointing to the memory address of I. I pointer also has its own memory address, and if I want to, of course, I can print out I by just printing out I directly or by dereferencing I pointer now. Okay, so both give 42. Incidentally, the one thing I mentioned was if I did this, cout, so C pointer, that is my pointer to a char. So what's going to happen? Any guesses? I did that up here with I pointer, right? This prints it out a memory address. This does not, but why is that, I guess? Yeah. Yeah, it treats it as a C string, right? So this is a pointer to basically an array of bytes in memory is treated as a string in C. And so that's what it's doing here. And if you look, if you print it, where did I put it? 2 ways to I. Oh, well, I guess it just, because I set it to null. Sorry. Let's go to address of C and then try that again. So it prints out H star and then stops. So yeah, H is obviously in the first location because that's that's the value of C, but then it's going to keep reading until basically it finds a terminator, which is like a 0. So yeah. All right, questions on any of that? Okay, good. All right, so you get all this. So yes, our new favorite operators are the star and the ampersand, right? So I can use them to declare variables. Here I can declare a pointer to an int. Incidentally, I often write this like this. Right? I might do something like this. So what are these two variables now? Because this is another thing that kind of, yeah. So A is a pointer and B is just an int. So like I kind of write like this because this is how like when I learned it, my sort of forged it into memory. But a lot of people write them like this, and that's because, well, now this is clear that, well, the type is int, this is a pointer, and this is not, okay? And if I wanted to declare two pointers, I would have to do something like this. So just be aware, my habits are kind of ingrained, that I always kind of write them like this, but in the back of my mind, I remember that, hey, these are, if I want to declare two pointers, I have to do it like this. All right. So yeah, this symbol now is a dereferencing operator as well as a declaration operator. Yeah, it's a good practice. If I have pointers that are not being currently used, they've either deleted them or I just initialized them, set them to null pointer. If you don't, sometimes there's garbage there, and then you try and dereference it, and instead of an error, which is nice, like it's like, hey, you made a mistake, it just works kind of, and you get some weird, and then you have a bug that doesn't show up until later. But if you set it to null pointer and then you try to dereference it, you're going to get a null pointer error, which is way better than a strange runtime error. All right, pass by reference, pass by value. Of course, this is an example we've seen before, slightly different. But here I am passing ints by reference because these are output parameters, right? So I pass them into a function, they get changed, and they come out. I can do the same thing with pointers, right? Let's run this really quickly. So P2, please enter a number. All right, so if I enter 55, double num returns 110. I just quickly, if I change these to pointers, well, then I have to change a bunch of syntax, right? So first of all, let's go down. When I supply this number, this no longer takes a number, it takes an address of a number. So I'm going to have to change this to ampersand. Double num will no longer take result, it'll take address of result. Down here, since this is now a pointer, I cannot just assign it this value. I have to dereference it first and say, and this will return the integer that it's pointing to, and then I can assign that a value. And be careful, because sometimes this can be not ambiguous, but like hard to read, right? If I have the multiplication and dereference and stuff like that. And this here also. So basically, every time I see an instance of n, I want to replace it with a dereferenced n, because I'm not interested in the value of n, which is just a memory address. I'm interested in the value of the thing that n points to. And then if I do all that, it should work just the same. And there we go. Pass by reference by reference. Well, this is now by pointer. All right, so as far as the compiler is concerned, nothing has changed, right? It will enforce the different types now, but in terms of what it's compiled into exactly the same code. But in terms of our syntax is now a little bit changed. But we can do the same exact things. Questions? Okay. All right, so we are into the dynamic memory allocation using the new keyword. So we needed pointers because new always returns a pointer. And when I call delete, I always want to call delete on a pointer, right? So You guys we've talked about static memory allocation. We've beat that subject to death. But, so yeah, now in C++, if I want to allocate an object, I want to allocate it and call the constructor. Well, usually, but yeah. If I just call malloc, it does not call the constructor. So we want to sort of avoid doing that, even though you can, right? Technically, C++ will let you do all this stuff. Class, we want to use new and delete. New will call the constructor, delete will call the destructor. And so yeah. Well, there's two types of dynamic memory really now. Right, so let's say I have an int. I make a new int that puts an int on the heap. I can assign it a value by dereferencing it, and then I can print it out. And I get 56. The other thing that I get is, what is it, P3? Is I get a definitely lost 4 bytes in one block. I got a memory leak. Okay, so right, you don't have to concern yourself for assignment 1 with this, but for assignment 2, if I see a new somewhere, I need to see delete somewhere else, right? Because otherwise you got a memory leak and you will lose marks for that. And there's a rule of thumb generally, and the rule of thumb is that, well, if I call new inside of a function, I probably want to call delete inside that function, right? There's exceptions to this, but I have to be very careful about them. If I call new inside of a constructor, probably in the destructor I should call delete. If I call new inside of an add function, in the remove function I probably want to call delete, right? This will help you keep in mind, it's a rule of thumb, it's not a law, but as a general rule, it works pretty well. I can also make a new int. Well, all these primitives also have constructors, so I can supply it a value. And then I can print out both of those things and delete them both. Run them with valgrind. I get 56 and 87, and I get no memory leaks, right? Because I deleted both of them. Questions? Okay. So this is a new set of responsibilities. The other thing I can declare is a new array. All right, so here I declared a pointer and I assigned it. Technically, this is the new square bracket operator, all right? So if you see like reference material, it will reference this. And this is how we use it. The type is here. So I've declared an array of 4 ints on the heap. And then even though I declared a pointer, I mean, we're getting sort of, if you want more detail, just ask. But so I'm going to kind of treat it lightly because I think sometimes digging into the detail is confusing. This is an array, and so I can access the array members by using the subscript operator, right? The square brackets. So I can say access whatever's in this location, and then I can print them out. Oops. Yeah, I didn't really mean to print that with valgrind. All right, so 0, 2, 4, 6. That is in my array. The one thing I didn't do is delete my array. Now, this is a mistake I make all the time. Okay, so I've declared this P3 with new brackets. I should delete it with delete brackets. Okay, so this tells the compiler, like, please go, this is an array. I know P3 is a pointer, but when you go to delete it, there's like an array of things there. So please reclaim all of that memory. So if I do that, everything still works, and I have no memory leaks. Of course, if you do things my way, which is you forget to include the square brackets, well, what do you think is going to happen? Any guesses? 'Cause I'll be honest, I don't know. This is, I believe it's undefined behavior technically. So it worked. It didn't even complain really. If I run with a Valgrind, I don't even have memory leaks, but it is, you know, it's giving me some warnings. Yeah. Yeah, so this is, again, these are like C-style arrays. So yeah, I was kind of avoiding that, but no, you don't. This technically is a dereference operation. So you can think of it that way. I can also use like pointer arithmetic, right? I could say plus I. Now, you will not see me ever do this probably in this class, but this, this is very common in C, and I'm pretty sure it'll still work, right? This P3, yeah, everything works fine. Yeah, so you can use pointer arithmetic. I prefer this. This is, I mean, clear is subjective, but to me, this reads nicer. I prefer it. This is, it starts to get pretty hairy in there, trying to understand what's going on. So yeah, that's, well, we've been introduced to dynamic types and dynamic arrays. Questions? All right, let me just draw a little picture of what we did there. So we had star P1. I'm going to stick to these two, int star P3. These are both pointers, and then I have the heap over here. And I said new int, which made a new integer on the heap, and this pointed to it, and I gave it some value. When I declared P3, I said new array of size 4. So that allocated an array of size 4 on the heap. That P3 now points to, and I can dereference, right? I can say P3 at 1, and it's going to, this will point to this location and give me back whatever value I find there or assign a value there. Okay, so this is, again, in the little scribbles, a little blob is a heap, and a stack would be something square. So this is basically what happened in that example in terms of memory. Questions? All right, I'm going to end it there and try to get to my next class on time. Yeah, I guess we have another class this week, so I'll see you guys later in the week. And yeah.